Today's lecture, in today's lecture, we are going to study a subject called bearing capacity and settlement. Why I said bearing capacity and settlement? I could have said bearing capacity only, but I want to stress on the term settlement because, as you will see, it is very important that we discuss settlement. It may be more important than bearing capacity. We will see that, and we will see that in the previous, maybe in the early years of geotechnical engineering, bearing capacity was enough. But later they discovered that settlement is more important than bearing capacity in many cases. So we have to study bearing capacity and settlement in the same time. Let's discuss what is bearing capacity. If you see this tower, it's a small observation tower on the sea. It is there. It is standing. It did not fall, but it is out of order. Why? Because it suffered excessive settlement. It suffered tilting. So these settlements affected this building. So I can call it that it has a bearing capacity problem, and I can be more specific in saying that it has a settlement problem because it's the problem of the soil. The soil is not adequate or is not strong enough to carry the structure. But in what way? Not in letting it fall, but in letting it suffer excessive settlement. So with this excessive settlement, the building is out of order. To study this, we have to study the soil. It's the load going to the soil. So I have to study the soil to see how much I can let the soil carry. Usually, to study anything, say in structure, you have to want to study, or in reinforced concrete, you want to study a beam. You simulate the beam to be an element in a finite element program, and you put the loads and study it. But in soil, it's a little bit different. What is the soil element? How I'm going to study? What is the material? How is the soil going to behave? Soil itself is not one material. It's many materials with different percentages. So you have many constituents, and the percentage of each constituent in any sample differs from the other. So it's a big problem. How can we study it? So this is one thing. The other thing is, what is the mode of behavior? Okay, I will say that this this triangle is an element. This triangle below the load is an element. How it's going to behave? When I push it, is it going to settle down, to be compressed, or is it going to behave as a solid body? So what happened is that in the early days of geotechnical engineering, scientists proposed they have to try to simplify any geotechnical problem into something that we can deal with. So they said that for this case, you have a load here. Let's divide the soil below this load into 3 parts and try in these 3 parts to have similar behavior. You expect that all soil in this body will behave more or less similar to each other. So they said this triangle below the load is affected by the load. If you push something in the ground, it will push a portion of the soil below it. And this portion will be as if it is hiding below this foundation. So this small triangle, they consider that it will behave the same. It will behave as a one body. It's not going to be compressed. It will move as if it is one block. So this first block here will what will happen once the load comes? This will try to penetrate, to go down. So this small triangle will try to penetrate the soil. To penetrate the soil, what will happen? This triangle will push this wedge to the right and the other wedge to the left, or all around. It is going to push this wedge. So this wedge is going to be pushed by this one. When this is pushed, this number 2 is also will be pushed by number 1, and so on. Number 1 will push anything above it. So you may have soil heave here at this location. So this is a trial from them to simplify the behavior of the soil. Based on this, I'm going to deal with blocks. I'm going to deal with block number 2, block number 1, and this small block, say it is block number 0, which is exactly below the load. So I will only deal with the interfaces. If you remember the blocks that we used to play with, small pieces. If I want to study the effect of one block on the other, then I have to study the edges, the boundaries. So I need to study this boundary between, say, number 1 and number 2. So this boundary, if I study it and I know how it is going to behave, then I can study the behavior of this whole problem. Because if I know what will happen between 1 and 2, so I will know what will happen between 1 and 0, and I will know what will happen between 0 and the foundation itself. So they found that we have two things. We have, but by the way, bearing capacity is the ability of soil to carry load. This is based on something called shear strength. Shear strength is the shearing capacity of the soil. How much can the soil carry shear? To understand what is shear, if you stand on water, what will happen? You're going to penetrate the water. You're going to shear the water. Why? Because water does not have any shear resistance. Anything can pass by the water. But if you stand above the soil, you can stand. You're not going to penetrate soil. Why? Because there is shear between frictional forces, something like frictional forces between, it's not only friction, it's friction and something else, but there are forces between the particles itself that prevent you from pushing whatever below you. Because when you stand on water, what will happen? You push the water particles below you, and the other particles next to them, they are not going to do anything. They will stand, like Arab countries. They don't do anything to any neighboring country. They stand. There is no shear between countries. If there is shear between countries, then they would be one block. So in water, there no shear, no interaction between particles. But in soil, there is some interaction. This interaction is called shear. We'll concentrate on this in the next slides, but from this slide I want to take from it that I have something called frictional forces and cohesional forces. By the way, frictional comes from the phi of the soil. Cohesion comes from the C of the soil. So C and phi of the soil both contribute to the shear strength or the bearing capacity of the soil. So it is the shear strength of the soil. So this line is not going to slide on each other. The above particles and the lower particles are not going to slide, but they are going to adhere to each other because of friction and because of cohesion. So this is what we are going to see here with some examples. Now we know that we have shear strength, something called shear strength. It exists in the soil, and this shear strength has, it's either friction, it's either cohesion. So let's understand what is friction and what is cohesion. So look at these two slides. This is a raft. This boy is pulling this raft. It's sliding on the ground. But here, his sister and his dog are on board. Here, there is no one on board. Which is easier for him to pull? Pardon? The empty one, of course. This is very strange. Why? Usually in structure, if I tell you I have a force, give me يعني اعمل تحليل. What is what do we call it? I want this force to be resolved into two forces with an angle. So usually I can tell you, if I'm pushing the ground with an inclined force, what is the effect? What is the perpendicular effect on the ground? You can take the force and use the sine or the cosine of the angle and use it. But if I tell you I have a horizontal force, what is the component of the horizontal force in the perpendicular direction? Zero. Because actually you are going to use 90 degrees, and 90 degrees will end up with multiplying by 0. So we'll end up having 0. But in our case here, this boy is pulling horizontally and the load is applied vertically. So in soil we have something different. We have forces affecting each other, or forces affecting the perpendicular direction, which is not a structural behavior. It's something related to soil mainly. So here we know that friction is affected by vertical force. So if I need to pull something and this something is very, I cannot pull it, reduce the load. We usually say that a car is in problem and you want to push this car and it is loaded. Tell you, okay, unload the car, let's push it first, and then once it is working again, put the load again. So you reduce the load to push something, to reduce the friction. So this is the first thing. The second thing, this person is sliding on ice, and here on grass. Which is easier? The first one, of course. So it depends on the material. The material affects the friction. So
not only the material, not only the material of the ground, but also the material that is used upon.
yes. The two materials that are in contact. If I'm sliding with like what happens sometimes, you are wearing a special type of shoes and you slide on the ground, and then you change with another type that adheres to the ground. So it depends on not only on the ground, on what you are wearing to move on the ground. So any two material in contact with each other, they affect each other in terms of friction. So it's the type of the material and the vertical force. So this is about shear. How can we calculate the shear? Just quickly, because now the shear, we know what is the shear, but can we calculate it? We said that we know the information that, friction. Friction is depending on the phi, the angle phi. How can I get this angle phi? In the Egyptian code, they gave us something related to, this is the translation of this table from the Egyptian code. They gave us the number of blows of the, you remember the SPT test that we do in site investigation? This SPT test, once I go with the number of blows and I go here, this is the phi angle. So say from 10 to 30, it is 32 to 36 the phi angle. So suppose I have not 10 and not 30, it is 20. So it is in between here. I can use ratio and proportion, and this is only a guide. It's not very accurate. There are tests that we can do to get this value. The problem is that if I take a sample to the direct shear that you've done last year, you remember that we can measure the phi angle. But the problem is that the direct shear is not accurate because the sample itself is not accurate. I did not bring the sample as it is from the side. It was distorted. So it is better for me to try to deduce the phi from something on site. What is on site? SPT, the n value. I take the n value and try to get a relation. This relation is based on lots of experiments and lots of researchers. They reach these values. They are more or less accurate. We can do, usually we do lots of tests. Use the shear strength test to get the phi. Use this to get the phi. Use another thing to get the phi. And finally, I can make an overview of all of the results and check which is better for me to use. So anyway, this is how we can get the value of phi. Now we go to another property, which is the cohesion, the C. What is the C? This is our model. This is a clay model, something made of clay. They shape this like a C. Can you do this with sand? Of course not. So it's only clay, silsal, that we used to play with when we were small. So why? Because it includes something else other than the phi, which is the C, the cohesion. So now you can understand what is cohesion. What is the difference between cohesion and friction? Friction is something like this. Cohesion is something like how you can bend a piece of clay to have a certain shape. Because particles stick to each other. But in the other, particles slide with friction on each other. So this is a completely different behavior. So let's get to the conclusion. I can have cohesion and I can have friction. Friction with sand, cohesion with clay. Bring some sand, pour them on the ground. They will take this pyramid shape. This pyramid shape because of the friction on the surface of the sand particles. They did not just fill the ground. No, they tried to keep on each other to make as much as possible, as high as possible. But some pieces fall to the ground, so that it took this shape of a pyramid. Cohesion is another thing. Cohesion is how we can shape the particles because they abide to each other. So these particles we see in many potteries and many things around us. So this is pure cohesion. And this is pure friction. And of course soil is not always pure cohesion and not always pure friction. It is a mix between both. So we have friction and we have cohesion in any soil, in most soils. So let's just imagine something. This will be the end of our introduction to understand C and phi and friction and cohesion. You remember the beads and البلي اللي كنا بنلعب بيه واحنا صغيرين. These beads that we used to play with when we were small. Imagine that these are the soil particles. Use different sizes, big, small, but they are all very smooth from outside, and they are they stand alone. Each particle stand alone. If you bring something, put them on the ground, you will never find two on top of each other. You will always find each one alone. They may fill the ground. So this is an imagination of soil particles with no friction and no cohesion. So this what would happen with soil if you don't have friction and cohesion. Suppose you want to add some friction to this material. Take these particles, bring any abrasive material, samphara, and try to induce friction on the surface of these beads. The more friction you can do and the more rough surface you can reach, you put them again on the ground, you'll find them a little bit taking the pyramid shape. A little bit. I'm not saying 100% like the sand, because these are big particles. So it will. So now we can understand how we can add friction to the soil. So add roughness to the surface. This is friction. Now cohesion. Bring some glue. Add them on the surface. Wait for a while so that this glue starts to be strong. Then put them together. You can shape them any shape. So cohesion is something that sticks the particles together. It's either material bond or maybe by electric charges, positive and negative, like in clay. In clay, the adhesion is the cohesion is because of this charges. So this ends up what we our understanding for the cohesion and friction. Now we said that we are going to study this to prevent or to reduce the settlement, or to deal with the settlement in a better way. Just to remember, maybe you've seen this slide before, that we have three types of settlement. Either I would be very lucky and my building will settle as one piece, or one block, or I have the building tilting because the settlement from one side is bigger than the other, like the Pisa Tower, or I would be in a very bad condition because the building suffered lots of differential settlement and end up with cracks all over the building. So these are important. This is a similar case for a big crack in a wall because of settlement. So I have here, as we said in the start of the lecture, to study two things: bearing capacity and settlement. Before we go here, then we need to say a small introduction. At the beginning, they were calculating the bearing capacity. It ends up with big numbers. If I calculate the bearing capacity, they gave me some equations. I use these equations, calculate the bearing capacity, and the building is built. But they find that even after calculating the bearing capacity and following it, the building is still suffering problems. So at the start, buildings were one floor, two floors. The loads were not very high. Structures were not that sensitive. You did not have windows that if you have a millimeter that is twisted, your windows are not going to, it will be difficult to open or close them. Doors will suffer the same. Cracks will fill the walls, because our structures now are very sensitive to motion. The height of the building is very high. I have utilities and I have elevators going up and down, and it needs very, very strict vertical direction to, or paths to operate. So I need, buildings are now very different than what is before. So we need to calculate also the settlement. In this lecture, in the following slides, we are going to see how to calculate the bearing capacity. But before we calculate the bearing capacity, let's calculate first the settlement, know how to calculate the settlement of the building. I have a foundation here. This foundation ends up with this line, which is the boundary of the compressible layer. Suppose I have sand followed by rock. Rock is very strong compared to sand. So rock is not going to settle. If it settles, it will be minor, portions of millimeters, and sand will be settling few centimeters. So the difference is maybe 100 times in the case. So I consider this to be my end. This is the end of the compressible layer. So my compressible layer starts from the foundation, the bottom of the foundation, and ends up with this boundary. So H represents the height of the compressible layer. This height of the compressible layer starts from a DF, which is the depth of the foundation, below ground. So this level area below ground is not going to be affected by settlement because it is above the foundation level. Am I going to take this area? What are the areas that will be affected by the load below the foundation? As we said in many cases, if I have a foundation here, the load does not just go vertically down, it spreads. There is always a spread for the load. Because of what, by the way? It is because of shear. Because particles next to each other do not leave each other. They try to be, if you are pushing, the particles below you are going to move down, but they don't move alone. Particles next to them try to help them not to go down. So the load, once we go down, the load spreads and so on, spreads and so on. So this is the thickness of the compressible layer, which is H. But as we said, that the area of the compressible layer increases, spreads down as long as we go. To be in the safe side, take it 2 to 1. Of course, it may spread more than that, but 2 to 1 is the minimum spread for the load. If you have a load, the minimum that it will spread like this. So this area below the foundation is the area that is going to be affected by the load. Other areas are not important for me. So to calculate the settlement, it means that I should divide this into millions of layers, and each layer I calculate the stress on it, its area, and calculate the settlement, and then add everything. It's a lot of work. What is a good reasonable approximation? Take the area in the middle, exactly in the middle. What is this area? We can calculate if here is B by L, here it will be B plus something due to the effect of the dispersion, and L plus something due to the effect of the dispersion of the load. So it's easy to calculate. Here it is B plus 0.5 H and L plus 0.5 H. Okay, so it is easy to calculate. So this is the new area. So I take the load now. Okay. So now this is the area that will be affected. I can now take the stress here. The stress here is the load, which is P, divided by this area, this new area. This is the stress. This load and this area simulates everything above and below. Why? Because in the area above, it is smaller, so the stress is higher, and the settlement, of course, will be higher. But in the area below here, the area is bigger, so the stress will be smaller, and the settlement will be smaller. So if I add the actual case of all these correct calculations, it will be similar to using this one and considering it that it starts from top to bottom. If I tell you that in the weight of the students in this class is 60, 65, 70. Then I ask you what is the weight of the students, you can tell me that it is 65 multiplied by 3. Just one number multiplied by 3, it will end up with the total, which was something more and something less. Sometimes you can facilitate the calculation by working on the average, not working exactly to calculate each layer. So it is easy to use this. My equation that I'm going to use, you remember that you have something called modulus of elasticity, the E of the soil, the E of anything. E is equal to the stress divided by the strain. This is known in the material, everything you know it. So it is the stress divided by strain. The stress is the load divided by the area. Load divided by area is stress. Strain is the settlement divided by the depth or the total length. If I tell you that this is the H and I have a settlement of 5 centimeter, so what is the strain of this layer? It is 5 centimeter divided by H. What I'm saying here is that I'm trying to deduce the rule that we are going to use. I can just give you the rule, I'll tell you, okay, use it and it will be okay. But I'm telling you that this rule is something trivial. It came from the ABC of it's the E modulus, stressed by strain, and it's not a big equation. You can deduce it anytime you need it. So this is, as I said, this is stress, this is strain. So the strain is this is the stress and the strain. It's repeated here. I should remove it anyway. Therefore, if ES substitute for the stress and the strain, it will be P by A divided by delta H over H. This will end up with this equation. This equation say delta H is the settlement, P is the load of the column, A is the area of the footing, the initial area of the footing. 1 over ES is the E of soil. H is the height of compressible layer. So if I use this equation, I just put H I know, ES I know, P I know, A I know, everything I know, then I will get a settlement. So now I can calculate the settlement of any foundation, knowing the load and the depth of the compressible layer and the dimension of the footing and the E of the soil. So if I know all of these parameters, I calculate the settlement of any foundation I need. Okay, so this is just one slide for how to calculate the settlement. Now, we'll go into some definitions to proceed to the next thing. We said before what are the types of foundation: deep foundation, shallow foundation. Shallow foundation consists of either isolated footings, combined footings, raft. The isolated footing is either square, rectangular, circular, strip, Just some definitions. Deep foundations, we have three types of, three major deep foundation. Driven piles, bored piles, caissons, which are the big types of piles. Just some definitions. Also continuation for this definitions. These things that we may need later in our discussions. What is contact stress? You know, what is the difference between bearing capacity and contact stress? Bearing capacity is the capacity that the soil can carry. But contact stress is the actual stress on the soil. If you are an athlete and you can carry weight, you can do weightlifting, we can say that the maximum that you can carry is 100 kilo or 150 kilos. So this is your bearing capacity, the maximum. But if I now tell you, please carry this 50 kilos and you carry them, then these are the contact stress. These are now the stresses that you are carrying. But maybe, not maybe, you can carry more than that. So contact stress is the actual stress on the soil due to the foundation. It may be less and it may be more than what the soil can carry. But in this case, if it is more, then we are on the brink of failure. Maybe failure would happen anytime. DF, which is the depth of foundation, the depth of the foundation from the ground, ultimate and allowable bearing capacity. There are equations that give us the ultimate bearing capacity of soil. The ultimate bearing capacity of soil is the maximum that the soil can take. More than that, it's failure. So what will happen? That you calculate the ultimate, divide it by a factor of safety, get the allowable bearing capacity. So the allowable bearing capacity is a factorized value from the ultimate. It depends on the code, it depends on your what you want. I have a very important structure. I will take a very high factor of safety. I have a normal factor of safety. I will just stick to normal factor of safeties. Modes of shear failure. As we said in the previous slides here, that to calculate the capacity of the soil, I have to propose a shape for the failure. I cannot just go and like this and start without proposing something. I have to propose how the soil is going to behave. So we said that this is one shape of proposed shape of failure. Scientists put these all of the shapes in three important types. Imagine that this is the foundation. What I'm going to speak now is this is called the general shear failure. General shear failure means that I'm just pushing this, as we said, that each area is a block. The area is not going to be compressed. It will act as a very stiff block. So this triangle is a block. This wedge and the other one all around is another area or another block. This triangle and this one is another block, and whatever above the foundation is another thing. So this is called a general shear failure. It means that the footing will push this one. Once it pushes this one, these two on the sides will be pushed laterally. When they are pushed laterally, they push this to move up and so on. That's why when you, by the way, this simulation, it may be strange, but it is more or less related to what we see actually. If you go on the ground and it is a little bit soft, maybe clay, and then you you find that your legs are started to sink in the ground. You will find that around your leg there is some heave in this ground. Why is this heave? Because of this formation. Because your leg here pushed the ground, and when it pushed the ground, the ground was pushed laterally, and the part that was pushed laterally pushed something vertically up, and we ended up with this shape. So this is the general shear failure. If you see that this general shear failure, it means that the load of the footing managed to survive from this block to this block to this block to this block. It means that all of these blocks are strong, because if one of these blocks was soft, then it will be compressed and it will not move the force to the one next to it. So here the general shear failure, it applies to strong soils such as dense sand and stiff clay. So this is the general mode of failure, but for soft soil. Suppose I go a little bit not strong, soft soil, a little bit soft. In this case, they will consider that the load will survive from this part to this part, but this will end up for the journey and the load will stop here. It will not affect any other part. So this is called local shear failure. Local shear failure is the same as the general shear, but the load does not go beyond this wedge. This is the end of it. Of course, this is for loose soil and soft clay. The extreme is very, very soft soil, very weak soil. So this is the shape. The load will only affect the triangle beneath the foundation. So this is called punching shear failure. So you have local, which general shear failure, which includes everything, or local for softer soil, or punching for very soft soil. This is just some information, because once we start doing a problem or something, we have to know which to use, which one to propose relative to the type of soil that I have. This is not an important slide. I may take it away because it will just make some disturbance for our way of thinking. Just ignore it now. It's good. But now it will not add. It's something to differentiate between the general shear and the local shear and the punching shears in terms of shallow foundations and deep foundations. But I'm not going to build upon it. I'm not going to use it for other information. So just if you care to read it, and we can discuss it individually with each other. So now we know we want to start. We knew everything now. We have all the data with us now. We now want the bearing capacity of the soil. What is the bearing capacity of the soil? This is the target of this lecture. To get the bearing capacity of the soil, scientists from the early start of the geotechnical engineering, like Terzaghi, they proposed many equations. Terzaghis equation, it uses something similar to the general shear failure. He proposed this. This is the footing, and this is the triangle beneath it. This is the radial wedge around it, and this is the passive wedge that is pushed to the top. Terzaghi proposed an equation depending on some factors. First, he proposed this is Q ultimate, which is the ultimate bearing capacity of soil. He gave us some parameter, but he said that this equation you can use it for a special type of footing, which is strip footing. If you have rectangular footing or square footing, then this will be the equation. And if you have a circular footing, this will be the equation. If you look at the equation, you will find that it includes something we know and many things that we don't know. C, we know that what is C, but NC, we don't know what is NC. Q, maybe Q is the stress on the soil. NQ, we don't know. Gamma, it's the density of the unit weight of the soil. B is the dimensions of the footing. NQ, it's also another parameter. So I have here something called NC, NQ, N gamma. These are parameters that Terzaghi must give us so that we can apply his equation. So these are he gave us these tables. You see, these are the equation and these are the table. He said that for phi from 0 to 50, these are the values of NC, NQ, N gamma of that you can use. So using the phi angle of the soil, if you know the phi angle of the soil, then you can get NC and phi and gamma. For me, this is just an introduction. Why? Because we're not going to study Terzaghi's equation itself. Of course, there's no. It's not only Terzaghi. There is Terzaghi, Meyerhof, many other equations. But what we are going to concentrate on here is the equation that is given to us in the Egyptian code, which is based on Terzaghi's equation. So it is as if we are studying Terzaghi. That's why we studied what is Terzaghi's equation. But we will take this equation. Q ultimate equal C, which is the cohesion of the soil, multiplied by NC, lambda C, IC, all of these are parameters, multiplied by gamma 1, and here gamma 1, and here is gamma 2. Gamma is, as we said, the unit weight of the soil, but they splitted it into 1 and 2 because 1 is for the soil above the foundation and 1 for the soil below the foundation. They use different types of soil. And the remaining, of course, the depth of footing, it is known. All of the parameters are either known or will be given by, here it will be given by the code in a special table. So let's just see what we have. NC, NQ, N gamma, these are factors that depends on the shape. Depends on the shape of the footing. If the footing is rectangular, square, whatever, it has different values. NC, NQ, N gamma, bearing capacity factor depending on phi. So these depends on the type of the soil, the phi of the soil. From tables, yes. See the cohesion, gamma 1 unit weight above foundation level, gamma 2 unit weight below foundation level, dF depth of foundation, B width of foundation, IC, IQ, I gamma, these are inclination factors. If the load is inclined, suppose that we have a load that is inclined on the footing. The footing is not perpendicular to the ground, or the load is not perpendicular to the ground, then in this case there are factors for the inclination. This is the main equation. We have here lambda C, lambda Q, and lambda gamma. This is the table given by the code. This is the translation of this table. Depending on the shape, it's strip, rectangular, square, or circular. I can take the value of lambda C, lambda Q, or lambda gamma. So just I go to open this table. If I have, say, I have a rectangular footing, then in this case I will use the value will be for these two parameters 1 plus 0.3 B divided by L. I take the dimensions of the footing and put it here, and I get the values. So it's just normal substitution in the table. The other, lots of tables like this. We are going to go quickly in these. These for NC, NQ, and gamma. We said that they are related to phi. So this is a table relating the phi angles. These are different phi angles, and these are the different values of NC, NQ, and N gamma. And so on. This is the rest of the table, because here it was to 27 degrees, here 42 degrees, and so on till the end of the spectrum of phis that we can meet in our design. Now again, this is for the I, which is the inclination factor. Also, these are equation that you are going to use to calculate the inclination factor. Of course, in the exam, I'm not going to try to see that you are good in checking a table and getting a value. I will try to give you the numbers as it is, but in your coursework you have to do it in your section lecture with your the additional in the tutorials. You are going to do it by hand. You are going to calculate it all throughout the year, but in the exam I will not concentrate on this, because I don't want you to start a problem with a different. Suppose that you made a mistake in the value of phi. Instead of taking it to be 32, you took it 23 under stress and in the exam, and you just switched the numbers. Then you will start with the wrong number, and I cannot consider the whole the whole situation as wrong, and I will have to follow your wrong number in your solution. So I prefer we will concentrate during the year, but in the exam then I will give you these numbers to use. And so on for all the parameters that we are going to use. It's either an equation or either a table. You substitute in this and get it. You will do this with your in your tutorial, and we can discuss it. It's either with me or with Rowan. Okay. So if I do this, then I have a footing. I can just get the dimension, the parameters and everything, and use the equation. I will get a bearing capacity for the soil. Is this enough? No, it's not enough. Why? Because the bearing capacity of the soil, it's for a soil of C and phi and special parameters. Suppose that you have multi-layers. Suppose that you have layer 1, layer 2 and layer 3. So which one I'm going to use? To be in the safe side, you have to check all of the layers. What will be the difference is that when I check this area, then I will use the parameters of this layer and the area of this footing. But if I go to layer number 2, I will imagine that there is another footing here, bigger footing, with lower stress, but different parameters, and so on. It means that to be in this, instead of wasting your time, if here layer 1 is the weakest layer and it has the higher stress, then I don't need to check other layers, because the weakest layer is subjected to the highest load. If it is safe, then all the others are safe. But the problem will happen if this layer is strong and it is safe. Then I have to go to the layer below, because it may layer 2 may not be safe because it is weaker. So it means that I have to check all layers till I reach the weakest layer. Once I reach the weakest layer and it is safe, then don't proceed more. This is just, of course, you're not going to face this in any problem, but maybe in future you will face something like this. Of course, the same here. You see this 1 to 2. 1 to 2 is the angle of dispersion of the load, that the spreading of the load will be 1 to 2. Now we have go to an example. This will let you understand everything now. Now we know how to calculate the settlement. We know how to calculate the bearing capacity. It means that. And we know all the parameters that we need, and we know what is C, what is phi, we know everything. It means that if we can use all of these parameters and put them in an example to solve and get the bearing capacity and the settlement, then I finished everything. So this is strip footing, cohesion, this all the factors that I need in my calculation. And these are the parameters that you get from the tables. It's NC, NQ, N gamma, lambda, CL, and I, and everything. So I've given you all the parameters. Of course, these parameters you can take from the tables. And this is the equation for the bearing capacity. I just substitute with the numbers that I get. Take the equation of the bearing capacity. You will find that here, of course, I should have added the main equation here, but you can just put it in front of you and just substitute in the equation. But here my concentration is not on how you can substitute. Of course, you can do it easily. But what I need is this. I reach this number. This number is the Q ultimate. This is the ultimate bearing capacity of the soil according to the equation. Okay? It means that at the depth that I have studied, because depth of foundation is one of the factors that you insert in the equation. So it means that, say at a depth of 1.5 meters, the soil can carry an additional load of 1,422 kPa. Okay, this is the total that the soil can take. This is the bearing capacity. This is the total bearing capacity of the soil. But the soil is already subjected to 1.5 meter of overburden pressure of the soil itself, because there is soil on top of it. So to be very accurate, then I should take this number and subtract from it the depth of the footing, which is here 1 meter, by 18, which is the unit weight of the soil. So this will be for just a minor change, but to be accurate, I have to take this portion away. Okay, once I take this portion away, I can divide by the factor of safety to reach the allowable, because here it was the ultimate load that the soil can take. Okay, so the factor of safety is either given or you assume it to be, say, 3, 2.5, whatever, depending on the code, depending on the importance of the structure, depending on many things. But not given, just take it 3 and it will be very good. So this number is the allowable that the soil can take. This is the allowable bearing capacity that you should have seen in a geotechnical report. In a geotechnical report, you find that they tell you the allowable bearing capacity of this site is so and so. Of course, it's wrong. It should be for the foundation. But anyway, because you have seen now that we use the dimensions of the footing. So now, once you get the factor of safety, you divide the allowable by the factor of safety, and you get this number, which is the allowable that you should have seen in a geotechnical report for the foundation. And as I said, it should be wrong. Usually I should give the bearing capacity for each individual foundation, because each foundation has a different dimensions and the soil beneath it is different. But for approximation, we can use one number, which is the safest number. Now we calculated the bearing capacity. We said that there is a case where the settlement is maybe more important, so I have to calculate the settlement. I use the equation for the settlement. This is the equation for the settlement. I start delta H of the equation is the settlement. Here I'm not calculating the settlement, it's the opposite. I'm trying to calculate the allowable stress that can give me the maximum settlement the building can carry. I know that the maximum settlement that the building can carry from the structural engineer, they tell me 2.5 centimeters. This is the maximum total settlement. So I substitute here with 0.025 meters. And then the rest of the equation, P by A, this is Q allowable. P by A, this is the stress. So this is the allowable stress that I want to reach. So I put it as something that I want to calculate, and I put the value of ES, which is the value of E of soil, it is given, and the depth of the compressible layer. Suppose that I did not give you the depth of the compressible layer. What you should do, you should take the breadth of the footing, multiply it by 2. Remember that previously we said that the stress usually penetrates the soil till it reaches twice the width of the footing. Below this, the amount of stress reaching the soil is less than 10%. So we can ignore it. So we can, if I tell you here, H is twice the B, I have a B of 2 meters, then I will study only 4 meters for the settlement. Then I will use all of this to calculate that my from the equation. Then I have the allowable stress. This is the allowable stress, 156. What is the value before that? From the bearing capacity, it was 400 something. So 468 compared to 156. Then what is governing me here? It's the settlement, because the allowable value for the settlement is 156. So now I will take the minimum value from both 156 and 468. Then the settlement is governing here, and I will take that my allowable stress is 156. I will now recalculate the whole, but based on a different B. I will take the B, instead of having a B 2 meters, it will be 0.8 meter. So I'm now using a smaller footing. I will do the same. Here you see this equation, the one I wanted to put in the one above. So this equation I will substitute again. I will repeat everything. I will not just discuss it here, but you will find that Q allowable here is 302. Q allowable here is from the settlement is 390. So from the settlement I get a bigger value for the Q allowable, which is more than the one that I got from the bearing capacity equation. Then I will use the one for the bearing capacity. So it means, as a conclusion, to end up this lecture, as a conclusion, to calculate the bearing capacity of the soil, then I have to do two things. I have to calculate the allowable bearing capacity based on the bearing capacity equation, which is the tradition in soil mechanics that we were using for a long time, and due to settlement of the foundation. I will get two numbers. I will use the smaller. Suppose in this graph I repeated this example 10 times, not 2 times, 20 times. So I will end up having lots of numbers, and these numbers change. Sometimes the governing is the settlement, sometimes the governing is the bearing capacity. Let's see. With a small foundation, the one that I have just said here, it was 0.8. This is the smaller dimension. In the smaller dimension, the governing was the bearing capacity. It means that in this zone 1, when I have small footings, usually the number that by the way, what is this line? This line is the line, the curve fitting of all the numbers that I got from the calculation. And this line also, this curve is the line of all the calculations that I've got from the settlement. So this is based on the bearing capacity equation, and this is based on the settlement calculation. So in small footings, usually the smaller number is for allowable bearing capacity. If I go a little bit up, it will be the settlement. But if I increase the breadth of the footing, the opposite will happen. Why? Because of the curve. If you go to something 2 meters here, suppose it is here, I will go up, I will cut the curve for the settlement before, and I go here, so the allowable contact pressure or the allowable bearing capacity is small. If I go to the curve for the allowable bearing capacity of the code, it will be a very high number. You have to understand this very, very important chart. This chart is very important in understanding how we get numbers in our soil reports. It should be like this. Usually in a very elaborate soil report, you should give me something like this, telling me for the foundation that you have, you should draw for this foundation. Suppose I need here to construct a foundation. You are going to assume different breadths, and each time you are going to calculate the allowable due to settlement and allowable due to shear, and draw the drawing and give me this. When I go to the office and I want to use your report, I will start, say, by assuming, and you assume that the breadth of the footing is 2 meters. I go with the 2 meters up, I meet here this curve for the allowable, I get the contact pressure. I design based on this, and I get the dimensions of the footing. If the dimension is similar to the one that I assumed, then I'm okay. If not, then I have to recheck at once. After this recheck, I will end up with having a number that matches my assumption. It's called iteration. You are going to do iteration. Usually you do 2 iterations, 3 iterations maximum to reach a very exact design. I will maybe stress on this in another lecture. We'll stop here because it's now more than 1 hour. Thank you.